Alright, so this is the review session that I was talking about for chem335. I kind of redid a previous version of the review session, and I think I added a lot more maybe helpful details. Previously, there were a lot of the reagents were omitted, and I used to think that was good because you could fill them in, but maybe it's a little better to have some of the reagents and maybe some of the little, not the full mechanisms, but maybe some of the mechanistic details identified. A lot of what this is trying to do is kind of identify like which reaction mechanisms might be useful for you to study, because not all of them are interesting to me. So I do that also. And the other thing is really seeing kind of a bird's eye view of all of the reactions and things we've learned, because this will really be helpful for the cumulative final. So let's see. Oh yeah, also I would recommend downloading this from the website beforehand, and you can kind of follow along while I'm going through it. And if you have a tablet where you can edit or add text, that might be helpful to you also. Alright, so let's see. This really focuses on the reactions. A lot of things like conceptual points, NMR, physical properties are not covered here. Now, if you need help on things like NMR, you should come to office hours and we can do that together. Certainly being able to do the NMR problems on the practice exam would be really helpful too. Mechanisms and reagents generally omitted. Now this is actually false. I put a lot of the reagents in, and for the most part mechanisms are not provided here, but you can certainly fill them in, maybe on paper or on the PDF or something. Mechanistically interesting. So I try to like if it's something that I think the mechanism is kind of cool, star. If it's very mechanistically interesting, that might be 2 stars or maybe even 3 stars. Like those are the ones you might really want to practice a bit in anticipation for the final. On the exam, we use these abbreviations for a lot of types of reactions and reagents. And if you can't remember a reagent, you can always fill it in as bracket O bracket for oxidation, bracket H bracket for reduction, P is protection, DP is deprotection. Often you can maybe start with that and then hunt around and find the actual conditions maybe elsewhere in the exam. Alright, so the main outline is going to be this. First we're going to talk about ways to form carbon-carbon bonds. We call that CC bond formation. Then we're going to go into cleavage of bonds, which we'll call CC bond cleavage. There's not as many ways to cleave bonds as there are to make them. And then we're going to get into a class of reactions called functional group interconversion, FGI, which means we're taking one functional group and converting it to another. So it might be an alcohol to a ketone, like an oxidation, maybe some of the alkyne reactions where you convert an alkyne into a aldehyde or things like that. But basically the interconversion of functional groups, we can just make that its own little category. All right, FGI. Homologation, degradation, just a little category of reactions. What do these mean? Homologation means like adding 1 or 2 carbons. Usually we think of like a 1-carbon homologation, adding a single carbon. A degradation is a reaction that loses carbons. All right. We'll have a little section on protecting group manipulation, like learn a little more protecting group stuff, and we have a little section on protecting groups, putting them on, taking them off, and kind of where you might see them. I have a little section on aromatic chemistry, the earlier stuff, electrophilic aromatic substitution, EAS, or also the Sandmeyer reactions. These are the new ones that we just learned about, the diazonium reactions, the N triple bond N, etc. I have a section called reactions with strange mechanisms. This is pretty nice. These are we just consolidate all the reactions with strange mechanisms in one little section. And for the most part, those strange mechanisms are kind of cool for potential exam questions. All right. let's see. Oh yeah, and there's a little bit of redundancy. I mean, some of these sections, some things are overlapped a little bit, but that's okay. Uh, but this is a pretty good outline of all the different types of reactions you've learned throughout the course. Okay, so now we're going to enter CC bond formation, and first thing we're going to do is talk about nucleophilic carbon, which are, generally speaking, that's Grignards. Well, organometallics. How many different kinds of organometallics? Well, kind of two. I mean, Grignards and lithiums do basically the same thing. Organolithiums, organomagnesiums, also called Grignard reagents, they all kind of do the same thing. But there's also the cuprates, which are their own kind of weird class of organometallic reagents. Back to CC bond formation, we also talk about enolate alkylation. So if you got an enolate or a ketone and you want to attach something next door to it, enolate alkylation. How many different ways can we alkylate and enolate? We'll talk about that. Alkynes. This back to the earlier stuff and exam 1. Alkynes can be nucleophiles, and that's a way to make CC bonds, and we'll review that, how alkynes can do that. Acyl anions. This is one of the last things we talk about in the course, and sometimes we can't even reach it, and sometimes it might be an extra credit type thing. If that's the case, we'll announce that, and you can watch a couple videos that I can give you links on. It's a really cool idea though. Acyl anion. That means kind of like a negative charge, an anion on a C double bond O, which is a very weird concept. We call it acyl anions, and we'll talk about that a bit. Whether or not it's on your exam, it depends on how far we get in the lectures. Carbonyl condensation. So this is like another class of CC bond forming reactions. That nice division. So this will include things like the aldol reaction, the Claisen reaction, which is one of the last ones you learn about. There's also kind of a twist on the Claisen called the ketone mixed Claisen. Depending on when you're watching this video, you may not have seen this yet, but you'll learn about it in class. It's just a slightly different variation of the Claisen. Of course, the Michael and the Robinson go hand in hand, and we'll talk about those also. Okay, so where to begin? I think CC bond formation is a great place to begin because it's a great way to build molecules. We can, start with small building blocks, attach them, and start creating larger, more complicated molecules, and then deal with things like functional groups later. The other thing is you actually learned Grignard in Organic 1, or you should have, and so it's a good place to start because we build on top of the concept of Grignards. All right, so a good place to begin would be the Grignard attack of a ketone, and it makes an alcohol in this case. And I'm not showing the mechanism, but the mechanism is actually pretty easy. The Grignard, usually I'd say phenyl dash MgBr, circle the dash, go attack the ketone, electrons go up, you get an O minus, and then you would protonate that O minus with like water or something, and you get the tertiary alcohol. And of course, from Organic 1, you also learned about other things you can attack, aldehydes, for example, and formaldehyde, and those make different products. This is a tertiary alcohol. Sometimes you get a primary alcohol, sometimes you get a secondary alcohol, sometimes you get a tertiary alcohol. There's also epoxides, and I'll show a review of epoxide attack in a second. All Organic 1, but it's a good place to build upon, and we do that in Organic 2. What you did not know from Organic 1 likely was that Grignards also attack esters. And when they attack esters, it's the same kind of attack. In this case, it attacks, electrons go up, electrons go down, electrons kick off the O minus. You can always fill that in if you like. And if you first actually get a ketone, and then the Grignard attacks again, and you get a tertiary alcohol. Technically, in this intermediate, this is an O minus, and then eventually becomes an OH, but that's not a big deal. Acid chlorides do the same thing. So when you have an acid chloride, Grignards attack twice, and you get a tertiary alcohol. But with acid chlorides, cuprates attack once. So you would if you have an acid chloride and you use a cuprate, it stops at the ketone point. Okay. So frequently follow-up water steps will be omitted. In each of these cases, water is like step 2, mostly to make this as straightforward as possible. I'm trying to eliminate things like that, and not bogged down on little details like that. But yeah, each of these reactions, there's a water step afterwards. All right. In addition to attacking ketones or esters or acid chlorides, another cool thing we learned was that Grignards attack nitriles, and when you attack a nitrile, it does the same thing. Phenyl-MgBr attacks the carbon, breaks the triple bond, makes a double bond, and you get this kind of intermediate. And then usually the step 2 would be the acid water, and then it would essentially protonate twice. So you get 2 protons, make something called an iminium, and the iminium is actually an RSCC also, and then water would attack the RSCC, and then a couple steps and you got the ketone. Kind of back to organic 1 a little bit. Epoxides can be attacked also, and so the big difference between kind of all of these above is that when a Grignard attacks an epoxide, it opens up onto the neighboring carbon, so you can see where the phenyl is relative to the OH. It's on the next door carbon. And how would that differ from attacking like this aldehyde? Well, the product would be the same, except if you attack the aldehyde, the OH would be right there. Of course, you can make epoxides from reacting alkenes with MCPBA. We'll see that a little bit later. Just for fun, a little bit of kind of thinking about how you could maybe use a Grignard to accomplish this little transformation. Cyclohexane 2 carbons OH to cyclohexane 3 carbons OH. How would you do it? Well, first you got to make a Grignard, and to make a Grignard you need a bromide, so it would be the reagent PBr3, and makes a Br, and then magnesium makes a Grignard, and then how many carbon piece are we attaching? A 1 carbon piece, a 1 carbon ketone aldehyde. Well, you can't have a 1 carbon ketone; it'd have to be a 1 carbon aldehyde. And it's formaldehyde, so it's the 1 carbon aldehyde. That would be a way to do this little thing. How would you go from 1, 2 to 3, 4? You'd identify the squiggly line. It's the same sequence: PBr3, Mg, and now a 2 carbon piece where the OH, since the OH goes onto this neighboring carbon, what would it be? It would be a ketone, aldehyde, formaldehyde, epoxide. Yeah, this would be an epoxide, a 2 carbon epoxide, and kind of the same kind of thing we did here, but it would be the 2 carbon version of it. What about, and this is an organic 2 reaction now, same thing, but if we wanted a carboxylic acid, same thing, PBr3, Mg to make a Grignard, and then a 1 carbon thing that if you attack it, you get a carboxylic acid, and we learned this recently in organic 2. It's CO2. So CO2 is the electrophile. So this bottom thing is kind of like understanding what are the different electrophiles that we can attack. All right. All right. So this is a slide that shows a little summary, maybe a really helpful summary for the different things that Grignards can attack. And we kind of start with the organic 1 stuff, and then we go into the organic 2 stuff. All right. So in each of these cases, the follow-up water steps are omitted because just to make it a little simpler on the structures and the drawing and everything to fit everything in. All right. So this is what you came in with from organic 1. That Grignards attack either aldehydes to make secondary alcohols, or ketones to make tertiary alcohols, or formaldehyde to make primary alcohols, or epoxides to make these alternate alcohols. Now, the big thing with epoxides is that the squiggly and the connectivity is 1 carbon away. So that's kind of the way you know that an epoxide is involved, is where the OH is, where the squiggly is attached, right? Okay, in terms of organic 2, this shows some of these newer organic 2 Grignard attacks, and we just showed the carboxylic acid one, which is very nice. If you attack a CO2, you make a carboxylic acid. If you may attack a nitrile, as we saw, you make a ketone. If you attack an acid chloride, it actually does it twice. And first it attacks, electrons go up, down, off, and then you get a ketone. And then does it again, where the Grignard detects the ketone, just like organic 1, and then you get a tertiary alcohol. Now you can see there's 2 things attached, little squigglies, right? And then if we have a Grignard attack ester, it does the same exact thing as acid chlorides. Okay, and the only different thing to remember is that if a Grignard attack, a cuprate, if cuprates attack acid chlorides, you get a ketone. It stops at the ketone. So what about cuprates then? So they're actually simpler because there's very little that they do. Only a couple uses of cuprates that we learned about in organic 2. So in contrast to Grignards, they attack 2 things. What are the 2 things that cuprates react with? Maybe you can think about that a bit. I just said one of them, acid chlorides. Acid chlorides make ketones, and the other thing are alpha-beta unsaturated ketones. And this kind of shows those two things. An alpha-beta unsaturated ketone, phenyl, basically phenyl ... attacks, kicks electrons up, make the enolate, and then you protonate the enolate to make a ketone. And then acid chlorides, like we said, is a NAS reaction. Phenyl attacks, electrons up, electrons down, kick up the chlorine, and you get a ketone. One of the things to note is that, and I think you saw this on one of the recent exams, if you do a cuprate and you're left with a ketone, well, you could theoretically do a Grignard now, and that would be cool because it's attached to different things, one at this beta position and then one at the oxygen position. But you can't do it the other way. It's not like if I attack a Grignard, if I start here and I attack a Grignard, well, that makes a hydroxy group and a Grignard's attached, but that won't react with the cuprate. So it's like it doesn't work. The best way to do that kind of thing is first you do a cuprate, make a ketone, then you do a Grignard, and then you make a tertiary alcohol. Okay, moving on to carbonyl alkylation. What that basically means is maybe starting with a ketone, which is a carbonyl. Carbonyl just means C double bond O, and then we're going to attach something at the alpha position. So first, sort of the bad way to do this is a very simple mechanistically. Just use a base, take off the proton, and go attack something through the enolate, and that, in principle, it looks really easy, and that's nice. You would get the ketone product. However, we often get like double alkylation, triple alkylation, and there's like other issues like that. So the yields are pretty low. So we call this a bad method, Chapter 18, bad method of alkylation. So then we learned about the improved method, which was the use of enamine. So enamine is it's alkene with an amine on it. Remember that if you react a ketone with a secondary amine, a little bit of acid catalysis, you make an enamine, and then the enamine can attack, kick off the Br. Now you got an iminium, and then the iminium reacts with water. The iminium is actually an RSCC, so you can just have water directly attack it, and then a couple steps and you make the ketones. This is a good, we see some little stars here. This is a good mechanism. It's definitely good practice, whether or not you see it on the final. It's often something we cover in the earlier exam, or like exam 2 or 3. So anyway, we call this an improved method because it usually works to give you a single alkylation step or product. Okay, other alkylation methods. This gets into some of the newer material, and one of the things you learned or will learn if you're haven't seen it in class yet is the malonic ester synthesis. So this is a pretty cool trick where you start with this thing called dimethylmalonate. It's a beta diester. So it's not a beta keto ester, it's a beta diester because there's two esters that are beta. Base alkylation. So it essentially attaches two things at the alpha position. And then we do ester hydrolysis. It hydrolyzes both of the esters from the beta diester over to the beta diacid, and then through a pretty fun mechanism, this flips around, and I don't know. It'll be in your notes, and if you haven't seen it yet, you will see it soon. Where basically CO2 is lost, and you're left with a carboxylic acid with two R groups. I would say this is a pretty good candidate for the final because it's a new reaction. The mechanism is not hard; it's just a few steps. There's also the related acetoacetic ester synthesis, which is another twist on this. This is essentially the same exact thing, and you use a beta keto ester, and methyl acetoacetate, I guess it would be called. Do the same thing, attach some stuff, you get this beta keto ester, and then ester hydrolysis makes the beta keto acid, which loses CO2 the same way. It should be in brackets like this one, but it's not. It's unstable. These are both unstable. Loss of CO2, and you get a methyl ketone with two R groups on it. Okay, quick review of alkynes. This is pretty old. There may be a little bit of alkyne stuff on the cumulative final, because definitely not on the new material exam. But just a couple things we can do with alkynes. A couple things we can do with alkynes that are CC bond formation. So, for example, if you have a 4-carbon alkyne, remember the big thing about alkynes was the terminal proton that we're not showing it is there. Can be removed because it's acidic, and a base can take it off, and then you can attack like an alkyl halide. So this is essentially an SN2 reaction. We can also do sort of the Grignard style stuff, like take off that proton and go attack an aldehyde. Now you can see how we've attached 3-carbon secondary alcohol. Or you could attack an epoxide. Take off the proton and go attack this 3-carbon epoxide. See the relationship of this alcohol and this alcohol. That just shows the relationship of attacking an aldehyde or an epoxide. Acyl anion. So again, this you may or may not have seen this yet, and it's often one of the last topics we do in Organic 2, and it's often an extra credit problem. So, but essentially, as you'll learn, aldehyde, or these are acetals and thioacetals. Remember the names of these protecting groups: acetal, thioacetal. But the big thing is that you can't really do this one because this is not a stabilized intermediate. But this one, when you use a base, take off this proton, and you have the thioacetal, with the dot negative. This is actually a resonance stabilized intermediate, and you can violate the octet rule because it's sulfur. Sulfur lets you violate the octet rule. So this is an okay intermediate, a relatively happy intermediate. And then what can you do with these things? And this is just a little example, starting with a bare bones thioacetal. You can use a base, take off that proton, and going back to the last slide, this can be a nucleophile. And it'll eventually relate to this concept of an acyl anion. Again, this will be in the lecture. So yeah, base takes off this proton. Then you can attack an alkyl halide, and we just attached this. And then you can imagine that we could do more. We could, if we wanted to make this, we could do it again. Base, and then maybe this phenyl CH2Br. Or if we want to attack a aldehyde, like benzaldehyde, it would be base and then benzaldehyde. Or if we want to attack make this kind of thing, what do you think it is? It's attaching this thing. Where's the OH relative to this squiggly? It was a ketone, aldehyde, epoxide. Yeah, this would be an epoxide. So it'd be, imagine the epoxide thing. So you can fill these in. Once we're done with that, then what can you do with the thioacetal when you're finished with it? Kind of two things. One, you can return it back to a ketone, which is sort of the normal acyl anion idea, mercury, water. Or you can do H2 rainy nickel, which is our way of reducing thioacetals, and basically just wipes it all off the molecule, and you're left with the alcohol in this case. Anyway, so yeah, this if you haven't seen this, you will see it, or I may refer you to YouTube for a extra credit problem. Moving onward, different CC bond forming type reaction. Let's get into the carbonyl condensations, and a couple of them. We got the aldol, we got the claisen, a couple more. So the aldol creates alpha beta unsaturated ketones. Those are the product of aldols. Sometimes it can be an aldehyde also, but usually we focus on the ketones. All right, so this shows a couple of the types of typical aldols. We have sort of the simple aldol or self-aldol, mixed aldol, intramolecular aldol, and it kind of shows the reagents are usually sodium hydroxide or like a base. And then how you get first you make a beta hydroxyketone in all of these cases, beta hydroxyketone. Loss of water makes the alpha beta unsaturated ketones. And if it's intramolecular, it makes a ring. Okay. Related to the aldol is the claisen, and this is one of the kind of newer ones you learned about. What's the product of a claisen? It's not an alpha beta unsaturated ketone. It's a beta ketoester. So that's a ketone that's beta to an ester. That's the product of a claisen, and this shows the same kind of thing. And if you have two esters react with each other, you can draw that mechanism. It's really not that difficult. Base takes the proton off, and then it just makes an enolate. It attacks the second ester, and you make the beta ketoester. You can do a mixed claisen, same kind of thing. Now, who's attacking who? Who can of these two? Who can be the nucleophile? Well, this is as an alpha proton, so this will be the nucleophile because it can make an enolate, ester enolate. This goes attacks, kicks off the ethoxy, and you can see how it forms this mixed product. And then in the intramolecular claisen makes a ring, and this makes a cyclic beta ketoester. The intramolecular claisen is also called a Dieckmann cyclization, so it's another name. It's the same idea of a claisen. They're synonymous. Intramolecular claisen is also called a Dieckmann cyclization, and it makes this intramolecular claisen. So try the mechanisms of these. These are really not that big of a deal. Make an enolate. In this case, you have to draw a second copy of the ester and go attack it, or in this case, make an enolate and then go attack this ester, or in this case, you can make the enolate and have it go attack this ester. Actually, the way we're drawing it, if you look at this, it's like this is going to be the nucleophile. It's going to attack the bottom's going to be the nucleophile, the top's going to be the electrophile. So make the ester enolate and then go attack this ester, and you get the product. Okay, so then there's also something called the ketone mixed claisen. It's just a variation on the claisen, and it makes a beta diketone. So it's two ketones that are beta to each other. So if you haven't seen this one yet, it's just going to be a twist on the claisen, and it'll be covered in class also. It's the same idea. It's the same idea, except the difference is that right here is like two esters are reacting together. The ketone mixed claisen, it's like a ketone is reacting with a ester, and you can imagine like this ketone reacting with this ester. Ketone is the more acidic proton, so the ketone's always going to be the nucleophile. Make the nucleophile, enolate, go attack, kick off this thing, and you got the beta diketone. A beta diketone. Product of a ketone mixed claisen is a beta diketone. And then there's another example. Okay, you got an ester, you got a ketone. Same molecule. And you can imagine, well, the ketone is always more acidic than an ester, and it will attack, and you can see how it kicks this off. So you could do mechanisms of these as well. These are the ketone mixed claisen and an intramolecular ketone mixed claisen. Okay, so the next carbonyl condensation reaction we'll consider is the Michael reaction. And remember that the product of a Michael reaction is called a 1,5-dicarbonyl, and that refers to two carbonyls that are on a 1 position and a 5 position. Remember also that sometimes a Michael will continue to something called a Robinson reaction and a Robinson annulation, and we'll see what would cause a Michael to continue to a Robinson in a second. For now, let's just show a couple of these sort of simple Michaels, and we'll do the top one and the bottom one here. And the top one, it's a pretty simple reaction, and you can envision how this alpha position on the ketone reacts with this beta position on the ester, and it kind of just attaches. And the mechanism is superbly simple. Base really takes the proton, makes an enolate. Enolate attacks the alkene on this molecule, and that makes the 1,5-dicarbonyl linkage. Okay, and then and you learned this in chapter 18, but there's also kind of like the other later version of the Michael, which is in chapter 23, using beta dicarbonyls. It's the same exact reaction, and you can see it's just a different nucleophile here that attacks this alkene and makes this product. These are both examples of a simple Michael reaction in two different chapters. So for any Michael, you should also consider which is the Michael donor, which is the Michael acceptor. The donor is always going to be the nucleophile and the thing on the left here, and the acceptor is the thing on the right, so the thing you're attacking with the alkene. And then same thing on the bottom. So how do you know if a Michael reaction is going to continue to a Robinson reaction? Because Robinson, we'll see that in the next slide, is it keeps going and does some more crazy stuff and it builds a ring. The main way you know if it's going to go on to a Robinson is if you look at the Michael acceptor on not the alkene side but the other side. If you have a CH over here, like a ketone, and there's a CH, that is usually the indicator that it's going to be a Robinson. It's going to do this enolate intramolecular aldol business. But this is an ester. There's definitely no CH there. There's a CH3, but this is not what we're talking about. We're talking about right there. This atom has to be a CH, CH2, or something like that. Okay, so let's talk about the Robinson now. This just shows a couple examples of a Robinson. Now again, just like with the Michael, there's sort of the chapter 18 or earlier version, and there's the chapter 23 later version. They're all the same. It's the same sequence. There's a couple steps. You've reviewed this recently. I'll show what those steps are. You might try practicing this on your scratch paper to see if you can make it over to the product. Remember, there's 4 steps. There's a Michael reaction, PT/reanalyze, where you switch an enolate from one side to the other, intramolecular aldol, and then dehydration, lots of water. Okay, so see if you can get through these reactions. Why didn't the Michael reactions on the previous slide go on to the Robinson? Remember, this shows the Michael acceptors and how we have a CH3 there and a CH2 there. That's kind of the indicator that it's going to do a Robinson. All right. And if you want to practice a Robinson going backwards, try this one. This is a good maybe final exam style problem. Or, I mean, you may see something like it. It's not necessarily going to be like show the full, all the steps. But if you can practice this and get it, then any kind of Robinson on the final you'll get. It says propose synthesis using Robinson annulation. Step backwards using the 4 steps. All right. Okay, so given all these carbonyl condensation reactions, we're going to play a game called Name That Reaction, where we're going to sort of go backwards. I'm going to show a molecule, and we're going to envision maybe what reaction type it is, and maybe see if we can step backwards to its starting materials. Alright? So, we see a molecule here. What type of molecule is this? Is this a alpha-beta unsaturated ketone? Is it a beta-ketoester? Is it a beta-diketone? Is it a 1,5-dicarbonyl? Probably the first of those, which is the alpha-beta unsaturated ketone. And so what reaction would it be? Should be an aldol, and that is correct. That's correct. That's an aldol reaction. And if you think about stepping backward from an aldol, the first, well, also I'm going to show a fresh copy of it with a squiggly line to show where usually where the thing is that gets attached in the aldol, and it's right through the double bond. Let's keep going backwards, and the precursor to an aldol is a beta-hydroxyketone, and you can see the beta-hydroxy group. And then if we were going to break this apart, it would be kind of the left, well, squiggly is between the alpha and the beta carbons, and you can envision like this will be the nucleophilic part of the aldol, this will be the electrophilic part. What will this be? What kind of molecules? If we break it apart, it'll be an aldehyde. So envision this thing with a double bond O, and that'll be an aldehyde. So there you go. And this actually shows a little bit of a abbreviated mechanism. So the ketone would be an enolate. Enolate attacks the aldehyde, and then you can kind of push forward from there. So that was a cool, simple example. If you have this thing, what do you think this is? What functional group pattern is this? Looks like we have a ester. You got a ketone that appears to be beta to the ester. That would be called, what's the name of that thing? A ester with a beta ketone, called a beta ketoester. Okay, and that would be what would be the type of reaction that makes a beta ketoester. It's a Claisen. Okay, and now where's the squiggly line? And so it's always going to be, with a Claisen, you're going to have an ester that reacts with another ester. And so we see this ester, that'll be maybe it comes from a nucleophile, and this will also come from an ester. And so it'll imagine kind of the left side with a ester, like a OCH3, or if we were using ethyl, we could use ethyl. So there's a squiggly line, and then we can kind of envision breaking this apart to have a right side ester being the nucleophile, left side ester being the electrophile. Nucleophile attacks, electrons go up, electrons go down, leaving group gets kicked off, and there you go, and that would make this product. What about this product? We're looking at it. It's not a beta ketoester. It's not an alpha beta unsaturated ketone. Oh, it looks like a beta diketone. What was the reaction that creates a beta diketone? And again, this, you may or may not have seen it yet in the lecture series, but if you haven't seen it, you will see it. But it's the variation of the Claisen called the ketone mixed Claisen, which is basically a ketone reacting with an ester. Kind of like just like the Claisen, except the nucleophilic side is a ketone. That's essentially it. So this is interesting because there's not like a clear single answer. There's actually two possible answers, and I'm going to just show approach A and approach B. So if I put approach A here, well, I can see, oh, well, here the right side's going to be the nucleophile, left side's going to be the electrophile, which would be an ester. Left side will be an ester. Is it going to be an ethyl ester? Is it going to be a methyl ester? It doesn't really matter. Just pick ethyl or methyl, your choice. And so then we can imagine that if we had a ketone, it would react with a methyl ester, and electrons go up, electrons go down, electrons go off, leaving group goes away, and you're left with a beta diketone. What would approach B be like? Well, it's the opposite. You just imagine the squiggly line being on the other carbon, and then the orientation of the nucleophile and the electrophile will be reversed. So in that case, squiggly goes the other side, and then you're going to break it apart. So now the left side is going to be the nucleophilic ketone part, the right side is going to be the electrophilic ester part. And there you go. So that would be this ketone reacting with this ester, and both strategies make the same beta diketone. Alright, so let's keep playing Name That Reaction a little bit more. What do we got here, and what type of reaction would make this molecule? Is it a alpha-beta unsaturated ketone? No, not. Is it a beta-ketoester? Nope. Is it a beta diketone? Well, it is a diketone. It's just not a beta diketone. But, if I was going to use Greek nomenclature, I might say it's alpha, beta, gamma, delta. Maybe a delta diketone. That would be, I never thought about that before, but yes, it's a delta diketone, also called a 1,5-dicarbonyl. And so, what is the reaction that creates a 1,5-dicarbonyl? Is it an aldol? Is it a clazin? Is it a ketone mixed clazin? Any other ones that begin with the letter M? It's a Michael. So this is a Michael reaction. This is what we call a simple Michael, because a simple Michael creates a 1,5-dicarbonyl. Alright? And so, and how does that work then? Remember, just like with that ketone mixed clazin we did, you can envision doing this two different ways, right? You can detach this kind of the acceptor and the donor one way, or the acceptor and donor the other way. And so we're going to do the A method and the B method, and this is the A method, and we're going to show the squiggly line between the alpha and the beta carbons right there. And then you can imagine breaking this apart to be kind of like the Michael donor on the left, which will be the nucleophile, Michael acceptor on the right, which will be the electrophile. And you can kind of envision this would be the mechanism, how the donor attacks the acceptor and makes the product. Okay, what would approach B be? Now it would be the same kind of thing in the opposite direction. So the squiggly would be right there, and then it's going to be the same exact thing. And oh yeah, where's the donor and the acceptor? There's the Michael donor, there's the Michael acceptor. And then if we have approach B, the squiggly goes the other way. And you can envision, do you see how it breaks apart and what the structure of the donor and the acceptor will be? Well, this will be the donor, this will be the acceptor, and the acceptor always has an alkene. So there we go. That's pretty cool. That's a nice way to kind of visualize the disconnection of this 1,5-dicarbonyl by the Michael reaction. Okay, next one. Okay, some kind of weird cyclic alpha-beta unsaturated ketone. This might be a good indicator of a Robinson. That's usually the case. So kind of thinking Robinson at this point. And there's our 4 steps. And let's practice going backwards. We've done this on the exams recently, so you know about this 4-step process. And if we're going backwards, the last step would be dehydration, and the precursor would be the beta hydroxy ketone. And then the next thing we're going to do is envision the squiggly line, and that's going to be the bond we create by step C, which is the intramolecular aldol. So when we draw this molecule, we'll just envision the bond go away, and then envision the enolate right there. This will be an enolate, and then this will be a ketone. So what does that look like? There it is. There's the enolate would attack the ketone, right? So that's stepping backwards through the Robinson. Okay, so with the next step, step B, is actually really easy. All you do is envision the enolate going the opposite direction. So all we did is put the enolate kind of there. And now, where's the squiggly going to be next? It's really between the alpha carbon of the remaining ketone and the beta carbon, and so we can see a squiggly line there. And so when we break this apart, this whole thing will be the Michael donor. This thing will be the Michael acceptor. But remember, Michael acceptor has to have an alkene. There will be right there, and a ketone right there. Other thing about the structure of the Michael donor. At first, we're going to have it be an enolate here, and then as we go back, it'll be a ketone. So, anyway, here it is. There's the enolate of the Michael donor, and there's the Michael acceptor. You can see how these two things come together to make this enolate here. And then I'm calling this step A part 2 because step A, the Michael really has two parts. The make the enolate, or the go to ketone to the enolate with the Michael acceptor. To do the Michael. This is the actual Michael, but then if we go back one more step, it'll be making this enolate, and so there it is. All right, cool. That's a neat little exercise. There's our donor, Michael donor, non-enolate form, Michael donor, enolate form. There's our Michael acceptor. Another fun thing we can do, just as a little shortcut to quickly visualize the Michael donor and the Michael acceptor. Let's use the same exact molecule we did, and then one of the tricks you can do is if you see the 6-member ring that is obviously being built by the Robinson, you can actually pretty quickly just draw squiggly through the double bond. That's going to be the aldol part of the Robinson. The other part will be the Michael part of the Robinson, and then you can immediately disconnect and actually show the essentially the Michael donor on the left and the Michael acceptor on the right. So this is a shortcut. We just quickly got from the Robinson product to the Michael donor and the acceptor in like 5 seconds. I mean, as long as you can see the 6-member ring and you know, and then draw the two squiggly lines in the right place, you can quickly figure out what the Michael acceptor is. All right.